Stand on any beach, and the ocean feels rhythmic and predictable. The waves crest, they crash, and they recede. Because of this, we often assume a tsunami behaves the exact same way, acting as a towering, curling wall of water, much like the ones we see surfers riding, only vastly larger. But a true tsunami rarely announces itself like a standard wave. Instead, the water simply begins to disappear. The ocean pulls away from the shoreline, aggressively draining outward, exposing vast stretches of bare seabed, stranding fish, and leaving boats tilted in the sand. Historically, this bizarre retreat fools people. Without the context of an approaching threat, onlookers treat the vanishing ocean as a sudden, fascinating marvel. They routinely walk out onto the wet sand to explore newly exposed reefs, or pause to take photographs of the strange anomaly. In reality, that dry seabed is nature's final warning. The ocean hasn't vanished. It has been drawn into an immense, invisible surge, gathering momentum far beyond the horizon, currently tearing toward the coast at the speed of a commercial jet. To understand why a tsunami behaves this way, we have to look at how water moves. The standard waves that lap against the beach are created entirely by wind pushing against the ocean's surface, churning the top layer of the water. A tsunami, however, requires a massive displacement of volume. Look at the mechanics. On the left, wind disturbs the top few feet. On the right, when the crust violently thrusts upward, it forces an enormous block of ocean out of the way. This sets the entire vertical column of water in motion, from seafloor to open air. Because the wave encompasses the entire ocean depth, it contains trillions of tons of moving water. Once that sheer, concentrated mass gains momentum, halting it becomes physically impossible. The chain reaction that launches this mass almost always begins miles beneath the surface, at the very bottom of the ocean, where Earth's tectonic plates meet. These massive, jagged sections of the planet's crust are in a state of constant, agonizingly slow collision with each other. When the rocky edges catch and lock together, their movement halts. But the tectonic drift behind them continues, forcefully compressing the rock and accumulating immense pressure over decades or even centuries. Eventually, the rock gives way. The massive plates snap past each other in a violent rupture, triggering a massive earthquake that instantly lifts or drops thousands of square miles of the ocean floor. This digital seismograph captures the extreme release of energy during one of these submarine ruptures. The violently spiking lines represent a deep-sea shockwave so powerful it physically alters the geography of the crust. With a massive volume of the ocean abruptly thrust upward by the shifting rock, gravity immediately pulls the water back down to restore balance. That falling water has nowhere to go, so it rushes outward in a rapid 360-degree ring. In less time than a blink, deep in the absolute darkness of an ocean trench, the physics of a continent-altering disaster are permanently locked into motion. Yet, if you were sitting in a ship positioned directly above this rupture, you would likely notice nothing at all. Out in the open ocean, the crest of a tsunami is often only 2 or 3 feet high. It rolls beneath holes completely undetected. Velocity defines the threat in deep water. Hidden beneath the surface, that column of displaced water is racing outward at over 500 miles per hour. Because the vast open ocean is thousands of feet deep, the wave encounters very little friction against the seabed. This lack of resistance allows the surge to cross thousands of miles of open water while maintaining nearly all of its original kinetic energy. For hours, it coasts as an invisible monster, a silent, high-speed transfer of energy through deep water, keeping its destructive potential entirely concealed until it finally meets the shallows. Approaching the shoreline, ocean depth abruptly decreases. The surge's front edge scrapes the seafloor, breaking from massive friction. Trillions of gallons trailing behind rush in at jet speeds, violently rear-ending the front. The wave compresses, suddenly spiking into a towering, unstable wall. This is why a tsunami doesn't strike like a normal breaker. Instead of curling, crashing, and washing back out to sea, it acts like a hyper-pressurized, high-speed inland flood that simply refuses to stop pushing forward. The initial height of the crest is lethal enough, but what ultimately levels cities is the unrelenting mass of the ocean continuously shoving that wall miles inland, crushing everything in its path. The horrific reality of this physics was broadcast to the world on December 26, 2004, when a massive magnitude 9.1 earthquake ruptured off the coast of Indonesia. Without detection networks, the surge blindsided nations. Dense neighborhoods were instantly wiped away, leaving bare earth and debris where thousands of homes once stood. 7 years later, the ocean struck again. This time, the target was Japan, a nation boasting some of the most advanced earthquake preparation and coastal defense systems on the planet. Incoming waves, some cresting over 130 feet, easily topped massive concrete seawalls. The churning whitewater aggressively bulldozed through coastal forests, swallowing entire municipalities. The floodwaters pushed deep inland, marooning heavy infrastructure. Modern airport terminals were suddenly surrounded by deep brown torrents, with airplanes and vehicles tossed like driftwood. The impact stripped away defenses of coastal nuclear facilities, triggering catastrophic meltdowns that poisoned the region and compounded the disaster with a severe technological crisis. These events demonstrate that even the most advanced coastal defenses remain physically outmatched by the raw, blunt force of a displaced ocean. Scientists now rely on deep water monitoring. Equipment like this NOAA ocean buoy constantly measures the water column, detecting millimeter-sized pressure changes indicating a passing tsunami. But technology only provides a brief head start. If you feel the ground violently shake or see the tides suddenly vanish, don't wait for sirens. The only correct response is immediate evacuation up a designated route to high ground. And survival requires staying there. The danger does not end after the first surge. Multiple waves can arrive over hours, and violently retreating water creates a lethal backsuction, dragging thousands of tons of heavy debris back out to sea. Right now, beneath the surface, plates continue their slow collision. The rock is compressing. The pressure is accumulating. The conditions for the next rupture are already building. We look to the ocean for beauty, resources, and life. But beneath the surface operates an ancient system of physics completely indifferent to the cities we build on its shores. A silent giant, always capable of redrawing the map in a matter of minutes.